The recording is on, so good morning or good afternoon, everyone, and welcome to this week's hot electronic seminar talk. I'm not going to say much. 1 hour talk, 30 minutes discussion. Keep your microphones muted unless you want to ask a question, and unmute your microphone to ask a question. Keep your video on if possible, and I think that's about it. Well, we'll be recording, and we are already recording, so keep that in mind. And okay, I think given the impact that Christian Sattler has had on this field, there's no other way of introducing Simon Huber than by saying that today's talk will be given by Simon Huber, and his topic is homotopy canonicity for cubical type theory.
Yes, thanks, Chris. Right, so if you look at this title, then maybe some people will be a bit confused because I wrote a paper with the name Canonicity for Cubical Type Theory, and somehow you would imagine that homotopy canonicity directly follows from that, and it of course does, but well, there's more to the story, so this is not exactly the same cubical type theory I will talk about. Anyway, so the overview of the talk is as follows. I will start with kind of a motivation of the work, where I will give some recap of cubical type theory, or sort of the basic ingredients of cubical type theory. I will talk about this just mentioned canonicity result, and then, well, cubical type theory is in a way a computational explanation of univalence, and it provides algorithms, and there are some choices in algorithms. And well, then I will go on with a proof of homotopy canonicity, but this uses a lot of machinery. So first I have to introduce some kind of semantical concept. What is a cubical category with families? I will give two instances of that. So there's the term model and the standard model. And then I will go over the technique of sconing for these cubical CWFs. And then we will be able to deduce the homotopy canonicity result. But I will, of course, go through this now. So let's start with cubical type theory. So this is just a quick recap. So this is a type theory which is based on a constructive model of homotopy type theory, which is based on a notion of Kant cubical sets. So this is the CCH, so-called CCHM cubical type theory. So this has some diagonals and connections, and there are all these also these reversals. But I mean, I will not really go into the technicalities like that. But this is really an active area of research. So there's several variants of these cubical type theories proposed. So here in the footnote, you see a few. I was too lazy to write out all the names, and it would also not fit the slide. So there's quite a lot of variants of this. There's also Carlos' hottest talk, where he talks about the new style of cubical type theory, sort of where you have Cartesian cubes as base. And well, there's lots of variants, right. And one important thing I think one should always mention is that, well, there are actually implementations of these cubical type theories, sort of in the sense that there are proof assistants which allow us to write programs in that and use it as sort of to formalize mathematics. So there's this cubicality, so this was our first prototype. There's now a flag to Agda, where you can use these cubical features, and the CMU people, they have also 3 prototypes. So there's red TT, red Perl, and yet another Cartesian cubical type theory. Right. So what is this cubical type theory? Sort of the basic idea there is that you have some kind of formal interval, so you can extend the context by this formal interval, variables ranging over this formal interval. So I will call these names, and you will have 2 endpoints in this interval. And then you can think of, if I have an element which is in a context with n names, this corresponds to an n cube of A. And then I can, of course, also apply a substitution. So I could set one of these names to 0 or 1, and this will give me the corresponding faces. So this is kind of where the cubes come into this cubical type theory. There's also machinery, sort of this is very technical. I will not explain this in full detail, but this will also reappear in the semantics. So in case you haven't seen this before, don't be worried. Though there's a notion of partial elements, and this is described by something called this boldface F, which is called the phase lattice or the cofibrant propositions. And what this does is we have a operational context which, given a phi in F, allows us to restrict the context. And then we have certain things in this F. For example, we have the proposition R equals 0 if R is in the interval. And then there's difference. This closed under disjunction and conjunction and so on. So this depends a bit on the variant of cubical type theory you're looking into, but there are several rules to introduce these Fs. And then a judgment in such a restricted context corresponds to a partial cube. So you only give particular sides of a cube. So, and the shape of what you have to give is described by this well, I call these also formulas, by these formulas phi. So for example, if phi is I equals 0 or I equals 1, this would just be the union of 2 points. So to give such a gadget will be to give 2 points. And then with this interval, we can also introduce the path type. So this is really what the Martin-Löf type theory is. The identity type is here. So the role is played by the path type. And well, a path is really like a function from this interval into A. So in the type theory, this is not actually a type, but you have formation rules. For example, you have given something which is a line in A, you can abstract it. So this is like an abstraction, read it like a lambda, and get a path from T0 to T1. And just sort of from the rules of how this, I mean, this really is like a lambda, so you have a beta and eta rule and so on. So just like how this behaves, you can justify reflexivity and function extensionality by just sort of the interaction of the lambdas and these name abstractions. And then there's another crucial ingredient, which is these so-called composition operations. And what they do is they give lids to open boxes. So for example, I have here an open box, so described by this Q, R, and P, sort of where I only given the lines, and a composition of this, so this is what I wrote here in red, is the dashed line above. And sort of the stuff which you put, how you describe the open box, so there's always kind of the bottom of the open box, and then the stuff you will also put stuff on the sides. This is really described by such a shape, or sort of one of these phase formulas. So in this case, it would be J equals 0 or J equals 1.
Sorry, are those arrows paths?
I mean, they're not, if you would abstract the names, they would be paths. But here I'm just indicating that the phase of Qi, if I set I to 0, it should be A, and if I set I to 1, then it's C. And similar here, this Pj is something which depends on a J. If I set J to 0, it's A, and if I set it to 1, it's B. Right, so as a special case, when you don't have any, and this phi corresponds to somehow the empty system or partial element, then you get the function from, if you have a dependent type, you get a function from A0 and A1. And this is really somehow the starting point to justify the elimination rules similar as we have them for identity types. And with this, we can also prove that this path type is an equivalence relation. And what is important here is that these composition operations are explained by induction on the types. So for example, if you have a product, then somehow product A times B, then the composition operation for this A times B will somehow involve the composition of A and the composition of B. So, and for all the type formers and the type theory, you will have an explanation of that. So you can write it in terms of something of the components of the type forming you're looking at. Another ingredients are these glue types. I will also not fully explain this, but sort of just mention why they're useful. So these glue types, they justify composition for universes. So they will be somehow, if I have this explanation for the type of a universe, then it will involve this glue type. But they also allow to justify univalence. And what it basically does, sort of the glue type is, if I have a partial equivalence, so this is something which is in a context, in a restricted context, so only on a partial cube, where this A is a total type and this phi is a partial type, sorry, the T is a partial type, then, and I have an equivalence, then I can extend this to a total equivalence. Sort of first I will get a type G, which is total, sort of not in the restricted type, and I will also have a witness that G is equivalent to A. And if I restrict this, that this restricts to W. Right. So this is a nice type theory. So it's has constructive semantics in a constructive meta theory. And this also, and well, this is also what we implemented. And then what I proved in my thesis is that, well, it satisfies the so-called canonicity property as follows. So if you start with a term of type natural numbers, which is only in a context with names. So it's a cube of names, cube of in natural numbers. So if you want to, usually this is just stated for where this is the empty context, which corresponds to points. Then, well, this term is judgmentally equal to a numeral. And, well, yeah, you can actually effectively calculate this. So a really rough sketch how this works is that somehow you first define operation in semantics. So this is something deterministic and typed in this case. So we're just on gadgets which are in only these named contexts. So we will define this on terms and on types. And so it's really important that somehow the computation will involve names, and it has to compute under a name context. So it really is important that the computation is formulated in this kind of name context. And then on top of this, there's some kind of computability argument done, which is somehow a very, well, it's kind of a standard technique for multi-enough type theory. And what I did is adapt this to this setting. So what you do is to say, well, when is a type, you define by induction recursion when a type is computable, and given a computable type, you say when one of this element is, when an element of type A is computable, and then you have to also define equality at the same time. But the definition here, well, and the definition for natural number will be such that you can reduce this. And then the argument will be, so everything is computable basically, and then somehow one gets this canonicity result. But a problem with this proof is really that it's quite involved. So this definition of these computability predicates there is quite long, and the problem really is that this reduction relation here is not closed under substitution. So if I have a line here which reduces to another, then I don't necessarily have that the points, the corresponding points are also reducts, sort of in this reduction relation. So this is quite involved, but well, after all, it gives in a way a very syntactic presentation of the model, and it tells us somehow that it's useful to use this as a programming language. And the computational content really in this, either in this cubical type theory, sort of to find this M here, either using this algorithm or this reduction relation or the concrete model. really relies on how this composition operation is explained. And also the composition for these gluings. But while we were doing this, somehow we noticed that actually it's not entirely forced how we define things. So there is somehow, when we explain the compositions for gluing, there's always somehow, there were choices. So we could do it either this way and that way. And then sometimes this also affected the efficiency of programs, the exact way how we did it. So we played around with this to make it more efficient. But then there's the obvious question. So actually, does this choice matter? So a priori, if I take different algorithms, so I could start with a term of type NAT, and then I computed with one algorithm to get a numeral, or I could use the other algorithm to get a numeral. But the question is this really equal? Right, so that's really the starting point, or the question we were interested in this work. And it's also connected to Voevodsky's conjecture. So Vladimir Voevodsky conjectured the homotopy canonicity for univalent type theory, so for MLTT plus the univalence axiom. And it states the following. So it says that, well, he formulates that there is an algorithm, but well, he states there's an algorithm given a closed type, a term of type NAT, which may use the univalence axiom. Then this, we can get a numeral and the path that this term we started with is equal to this numeral. And the identification we get may use the univalence axiom again. But this is here, then with numeral, I just mean successor of successor, successor of 0. And Mike Schulman proved a variant of this, where you somehow have a truncatedness assumption on all types. And his proofs uses a technique called sconing, which was really also the starting point for our work. And, right. So the general stumbling block for proving Voevodsky's conjecture is that somehow you want to use this gluing technique, and it's not clear, but the problem is that you will glue it with some kind of global sections functor, but there one needs somehow that the closed terms that give rise to the structure used in the model. So in the case of Voevodsky's model, it would be a Kant simplicial set. So it's not clear how the syntax gives rise to a Kant simplicial set. So right, so there's rumors that there's some progress in this, but well, I don't know exactly about that. Right, so we can formulate a variant of that. So if we look at this cubical type theory, where we take away all the computation rules for composition, and now if I start with a term of type NAT, closed, is it path equal to a unique numeral, or unique is actually not so important. Uniqueness follows from consistency. But anyway, so is it path equal to a numeral? And this is what this talk will be about, or the rest of the talk. And just as a warning, somehow this doesn't directly give us, can you still see me? Somehow my slides disappeared. Okay, anyway, back. Okay, great. Right. Where was I? Right, so this doesn't directly give us the corresponding statement for the system with those computation rules, that because if I start with a term U of type NAT with the computation rules, it might not be a term in the system where I have less definitional equality. So this is just as a warning. So this will not follow from that. Okay. So now I will describe how we prove this. So this will somehow be a sconing construction, and this is a construction on models. And so I have to talk a bit about these models, and sort of starting now first with the notion of a model of type theory. So this is pretty standard. So that's Categories with Families by Peter Didier. I forgot to put a reference, but I guess most of you know this. So a category with families, also CWF. So this is given by a category of contexts and substitutions. And then there's a pre-sheaf of types, sort of where the pre-sheaf action corresponds to substitution. And then there's a pre-sheaf on the category of elements of this of types. We have a terminal object, and then, which I denote as one, and then sort of the empty substitution, and then operation of context extension. So given a type, I can build a context which extends the current context by this particular type. Then I have the first and second projection, pretty standard everything, and I can extend the substitution, and there are some laws satisfied. What I will use in this talk is somehow a slight modification of this notion. So here something popping up in red. So there will be a bunch of further pre-sheaves on the category of context. So this is this TYN, which is now, this N indicates the level. So this is for universes. And I assume that these are sub-pre-sheaves of the pre-sheaf of types. So with this, I mean really pointwise subsets. And it is also cumulative. So if I have a type of level n, then it's also a type of level n plus 1. So this simplifies things later on a bit. Then there's also a notion of universes. So this now connects to why I have this hierarchy of pre-sheaves, or sequence of pre-sheaves. And sort of for such a CWF, to have universes means to have, well, first of all, types, which corresponds to the nth universe, which is a type of level n plus 1. So UN is a type of level n plus 1. So these gadgets should be stable under substitution. And the terms of this UN are just the types of level n. And well, there's sort of an action of substitution on this side and on the other side. So both of them should correspond. And then the rest of the structure is defined as usual. So you can define one CWF as pi types and so on, sigma types and so on. And sort of what we require is that they preserve the universe level. Okay, so based on this, so we will use this definition not as I presented now. So here was what sort of I said they're pre-sheaves, so there's something valid in sets. But what we will use this is, we will use them as an internal pre-sheaf. So they will be used internal to a pre-sheaf topos. So now I will talk a bit about this internal language. So I have an assumption that we have omega, so we have a bunch of growth-unique universes in our underlying set theory, and we have a small category C, and we work in the internal language of this pre-sheaf topos, and we very much work like Orton and Pitts did. And this internal language is a form of extensional type theory. So we also reference here sort of to Andy Pitts' hottest talk here. So these growth-unique universes, they lift to universes in this internal language, which is also cumulative. And in this pre-sheaf topos, we have a notion of propositions, so elements of sub-object classifier, and each such element gives rise to a type or object, which I actually also will just write with the same psi. And it's, I mean, it will be clear in the context. Right, and the element of this type here will be called star. Now, I also have a notion of partial elements, so similar to what we had in the syntactic theory, sort of for an object X, a partial element is given by a proposition which defines sort of the extent, so where it's defined, and the function from psi to x. And such a partial element extends a total one if, well, on the part on psi, it is the same as the total element. Okay, so now with this, well, we need some first assumptions here. So now I will assume that we have an interval, which is really just a presheaf with two endpoints, and it should live in the lowest universe. And I further assume I have some kind of an object f, also small, which I call the cofibrant proposition, or before I called them phase formulas. And each of these things should give me a proposition. So I have a mono from the cofibrant propositions to the subobject classifier. Now if I have so now I can talk about paths. So I have this interval, and if I have a function from I to the largest universe, so this is really sort of this omega is really there to talk about types in a way, or big types. And sort of given such a path in U omega, we can define the type of well, filling structure on this path. So that is this type has fill as follows. So it takes, this is the type of operations, so which take a phi and f, and then, well, this is 0 or 1, this b here, and it also takes a partial element. So now A is a type, so we're given an element in the interval. It gives me something in AI, but only on a certain part. So this is kind of corresponds to, well, yeah, it's a partial element. And so this is either on sort of, this is corresponds sort of the I equals B part corresponds to give the lower side of the open box, and the phi part corresponds to giving the other sides. And well, these operations should give me an extension of the input, sort of this S phi du gives me a total element, which I restrict, if I restrict it to phi, it extends u, or it's equal to u. And then I can formulate the type of filling structures. So now if I have an object x and a family over x, which is just a function from x to u omega, I can define fill xy as, well, for any path in x, for any path gamma in x, I get a path in u omega by just composing with y, and I require that this has a filling structure, or has this filling. So this is really very similar to, well, well, that's what OrComput's also used.
Sorry, can I quickly ask, what's U omega?
So U omega is in a way the largest universe. So this is somehow it's a cheap way to talk about big types in a way. So before in the CWF world, I kind of say that for any natural, I have a universe, and then there's also a universe in the presheaf world, which somehow corresponds to this Ty here. Did it clarify?
I mean, don't you usually just take a universe at some level, and then I don't understand why you've gone for the biggest one? Because I don't think there is a biggest one, is there?
Well, there is one which contains all the others. I mean, these UIs. I mean, I don't know much about the, I mean, depends on the presheaf topos. I mean, there might be other stuff in there.
All right, don't worry.
Okay, so now I'm ready to define kind of the modification of this categories family, so which we named cubical categories with family. So this is maybe a bit slightly ad hoc name, but we didn't come up with a better name. We couldn't come up with a better name. So a cubical CWF. So now this C, I, and F, they are parameters to this definition. So they're given by first CWF, which I denote by this con, hom, ty, blah, blah, which is internally to this presheaf topos. So in particular, this means, for example, that the contexts are now a pre-sheaf on C. So I will be given, for each object X and C, I'm given a set of contexts at stage X. And then similar types will be given an object X, a context at stage X, I'm given a set of types. And further, I require that the CWF has the structure we want. This is pi, sigma, natural numbers, and universes. And I will write this structure using this typewriter font. This one.
Wait,
here.
did you say the pre-sheaf gives you a set of contexts?
So I mean, con is an object in the internal language, right? Which means, so what
does it act on? So like, how do you get a set of, how do you take sections of that?
I'm not quite sure I understand.
Okay,
con is really just a functor from C op into Z.
Okay, so it takes each object of C and it gives a context.
No, it does give me the set of context.
The set of contexts.
Yeah.
What are these contexts in relation to?
It's just I mean, this is just somehow a structure you basically given an inhabitant of a certain type in this internal language. So you can write down in the internal language what it is to be a CWF, and then you just say, well, I have an inhabitant. I tried to unfold this a bit, what it means, but I should have prepared a slide of that. But maybe it comes later on. So later I will give an instance of that, and maybe this becomes a bit clearer then. Is there more confusion right now?
Maybe it'll clear up if you continue.
Okay. Good. So this is kind of the first assumption. So somehow we have a CWF, but now internal to this pre-sheaf topos, and we have a filling operation. So now I defined this on the previous slide. What is the type of filling structure? So this is respect to this parameter I and F. And I require that I have an operation which where I have a filling structure on this type here, right? So this lambda A Tm gamma comma A is really a function from Ty gamma into U omega. And then, well, I have a filling operation on this. And well, the filling operation should be, I mean, this constant should be stable in the substitution. So there's an action of these, of this hom here, right, on terms. And then there will be two more ingredients, which is dependent past types and glue types, which I will show in a second. Right. Actually, I will show now. So let's start with the past types. So these are dependent past types because, I mean, this fits what we'll do later on better. So we require here that we have operations. So given, if I have a path of types, so this is A here. So now this is really somehow, this is now operations in the internal language, right? So I have this path of types. I have two endpoints. This is now in TM. I have a new type called, this is the formation rule, sort of the path type. And to give inhabitants, I give, well, section of this type here. So I give, for each I and I give a term in A of I. And then I can abstract this gadget and get a term of the path type. So this is, so to build these gadgets, I will use the lambda of the internal language, right? Because I have to give a function from I into here, dependent function. This is really a bit like
Sorry, is I a representable functor in your pre-sheaf category?
Right now, I don't assume anything like that. So this will be an assumption later on. But I mean, for now, it's just defining. It's just a definition. So for the definition, I don't need any assumptions like that.
But I mean, I is just an object that happens to be there.
Yes, this is a parameter. So I assume I have I and F around. Right. So there was this path abstraction, and there's also a path application. So this really reflects the operations like we had before in cubical type theory. If given a path in A from U0 to U1, I can apply an element in the interval. The resulting term is called an app. And well, I have the required, the usual definitional equation. So this P should connect U0 to U1, and I have a beta and eta law for these gadgets. And there's also an assumption that, well, this path preserves levels, and all this stuff has to be suitably stable under substitution. Right. Yeah, I'm not quite sure. So this is more slides for the experts. It's kind of also internalizing this. I will probably let me maybe just skip this or not go through all of it. It's in a way internalizing this operation. So if you understood how we did this here, I mean, it's kind of clear how you would define this glue operation here. So you would given a total type, something in F, a cofibrillant proposition. Here, this T is a partial type. And then what I have here, this E, the input will be a partial equivalence, or equivalence is formulated using path types and contractible fibers. So you can write this out. We had the structure of pi and sigma and path types, so we can write down what an equivalence is. And then given all this data, we will get a new type, and which extends the type T. And then there's also another sort of, you will also get a function which goes from this glue to A, which extends the input equivalence, or well, actually only the input functions. Right, and then there's also a way to form elements in the glue type, and there will be beta and eta laws, which I will not explain in detail. But what I want to mention or stress is that somehow there's no equation how somehow the filling is explained. So there's just the assumption that there is a filling operation, but there's no equation which this filling operation has to satisfy other than that. I mean, the filling extends the input basically. Okay, so if you now assume certain things about I and F, so for example, if you assume that somehow this I has the structure like we had in the CTHM paper, so we have some kind of connections on it, there's a conjunction, and this F forms a sublattice of, this should be an omega. So you have this junction, conjunction, top and bottom, and it contains these I equals B, I equals 0 and I equals 1. Then this is really like in the setting of CCHM. Then what we can prove is that these path types, they justify almost the same rules as Martin-Löw identity types, but the only difference is that the rule for the eliminator J is only propositional rule. Sort of the computation rule is only propositional, so you're up to a path. And then you also can prove that the type is contractible whenever any partial element can be extended to a total one. And then using this, we can show that this function here is actually an equivalence. And giving us a model of univalent type theory where we have propositional computation for J. So with some structure on I and F, we get a model of univalent type theory. Okay, so now, right, so let me describe the term model. So this notion of cubical CWF is not quite generalized algebraic theories, because we had the subsetting, so this doesn't really fit the scheme. But we can also just directly, concretely give this and build the initial cubical CWF, which I denote by this T. So C, I, and F are fixed, and initial is with respect to strict morphisms. So I didn't define that, but it's kind of well, strictly commuting with all the structure we have. And then sort of this T is induced by, now well, we have to present somehow the rules, and the rules are rules for judgments. The difference kind of is, or the important thing is that the judgments are indexed by objects in C. And if I have a judgment at stage X, and I go from an action from Y to X in C, I can apply just some kind of substitution application. But in general, this T has infinitary rules. So I maybe not walk you through this completely, but I mean, to form a pass type, sort of the input here, the type here is given as a family of compatible types, say. So this is kind of at stage Y, you have to give the type AFR for each F and each R. But in certain settings, like with the De Morgan cubes, you can also present the rules in a finitary way. And kind of the rough correspondence is that in this setting of CCHM, De Morgan cubes, is that if you index by IJK, for example, then this corresponds to putting the names in the beginning of the judgment. Okay, so actually I don't want to say more about the term model, but this is the syntax we're going to prove the homotopy canonicity for. Right, but it's very, very close to well, the cubical type theory, but it shuffles around the names a bit. So next we construct something which we call the standard model. And for this, we need certain assumptions. So the first assumption is internal. So it will say that I and F, they satisfy the axioms of Orton-Pitts. So this somehow says that, well, 0 is not equal to 1. And well, you can read the Orton-Pitts paper. I will not, I mean, it's not important right now. I will not be able to go into this anyway. And then there's an external assumption, so which is that we have a tiny interval. So the exponentiation with the interval has a right adjoint, which also preserves levels. And this external assumption is satisfied if I is representable and C is closed under products. And like Andy also presented this in his hotless talk, you cannot make this adjunction internal. So this is contradictory. Okay, so with these assumptions, or with these assumptions, we can, well, first we can lift this adjunction to, or well, it descends to an adjunction between categories of types over U omega. Okay, so this is a bit confusing. Yeah, let me maybe go quick with this. You can see the details in our preprint or in this Licata Orton-Pitts Spitters paper. That, I mean, we have this Hess fill here, but the problem with the Hess fill here is that it takes a pass in U omega. But we can sort of, if we talk about global types, so global now with respect to the internal language, we can have a correspondence. So we have a type, sorry, an operation on types, which satisfies the following, that the global sections, so the global filling structures, they correspond to global sections of the C. Right, and sort of actually what we use is that we have maps back and forth suitably natural. And then with this thing, we can sort of, first of all, in the internal language, redo what Orton-Pitts or what we did in the CCHM paper. So we can construct these path types and glue types. In the pre-sheaf topos, we have that filling structures are closed under pi, sigma, path, and glue. So that's kind of what we did some years back. And then, but we can also then deduce that this C, operation C, is closed under those type formers. And we can define a type of, well, the fibrant universe, which is just the sigma type of all types of level n, which are given sort of, this really corresponds to having a filling structure. And then using gluing itself, we can show that the type of fibrant types is fibrant itself. So I call something fibrant if I have something in C. Then we can organize this data into a cubical CWF, which I call the standard model. So it's S, written S. And where the category of context now is this, the large types in U omega, and the substitutions are just functions. And types over gamma are just maps into this fibrant universe from gamma. And then the elements or sections of such a type are just the sections of, well, the underlying type. So the fibrancy structure doesn't matter here. And well, this is pretty sort of what we did in the CCHM papers, or also in the LOPS paper. But one thing which is important for what I'm doing, and I probably should hurry up a bit, is that we also have identity types. So identity types was the good definitional equality computation rule, the computation rule. And this is really followed by a technique by Andrews Won. So we can also define the identity type, which is also in the fibrancy structure on this. And this will be crucial how we will treat natural numbers in the scone model. Right, let's go to the sconing. So what we start with is we assume the same stuff as we did for the standard model, because we will use the standard model. And otherwise, we will just start with an arbitrary cubical CWF. So we have this M, denoted M, and the structure will just write as con, hom, and so on. And then what we're going to do now is to define a new cubical CWF, the sconing of M, which I write as M star, and well, consisting of con star and so on. And well, how do we do that? So first, note that the filling in M gives us an operation that if I have a closed type, a type in context, well, in the empty context, so one is the terminal object, then the terms are fibrant. Yeah, I mean, this is using this assumption that, sorry, this is this operation here, and then we apply this stuff from our standard model. And now we can define global sections. So that's what you usually do the sconing with. So you do this global sections operation. So how is this defined? So given a context, the global section of gamma are just the substitution from 1 to gamma. And on substitutions, it's defined as, well, just composition, precomposition with sigma in this case. And for types, we define this bar A, which is now a type over, a fibrant type over the global sections of gamma. And it's just, well, the terms, the closed terms of A. And these also have a fibrancy, so this fibrancy structure. But I usually will not really talk about the second component. I will just write bar A also for the first component here. And then this also extends to terms, and well, yeah, in the array I have written here. And we could really call this in a way a weak cubical CWF morphism from M to the standard model. Right, so because these are the types of the standard model, and weak in the sense that it only preserves the context extension and terminal object in a weak sense. not strictly. And on this sort of, now we can explain the CWF structure in the sconed model. So now the context is in the sconed model is given as a pair. So it will be a context in M and a predicate on the closed instances of gamma. And we really want to think as this gamma prime is a way of, is a proof relevant computability predicate. Substitutions are also just pairs, so we have given a substitution which preserves this computability predicate. And now this is the crucial definition here. A type in context gamma gamma prime is also a pair where we have first a type in M over gamma, and given this is a typo. Sorry, this should be bar gamma here. So given a closed instance of gamma, given a proof, so the prime stuff should say that rho is computable, then we have a predicate on the closed instances of A. And well, this should also be fibrant. And I will usually write this kind of as this bracket. So the fibrancy structure, I want to separate that. And a term or an element of such a type is just given by, well, given a closed instance of gamma, which is computable, a witness that the left side of this is computable. So let me repeat, so an element here is a pair of a term in M, and U prime is a witness that it's computable. And then you can define sort of context extension by just taking context extension of M, and then the computability predicate will just be defined well, as using a sigma type. And then you can define of the first and second projections and so on. And the rest of the CWF structure, sort of the basic CWF structure. I'm running out of time. Right, so let me just quickly sketch how dependent products work. So the assumption we have a type in gamma gamma prime and type B in the extended context. How do we define the product? This is again a pair, so this is always a pair of stuff in M. So this is just the product, the pi type in M, and the predicate for on the closed terms of the pi type is given as follows. So F is computable if, well, it sends computable input to computable output, right? So given A, which is computable, we have a witness for that by A prime, F of A is also computable. And then here the fibrancy structure is really derived from, well, what we know about the standard model. So we know that fibrancy is closed under pi types in this case. So this is really always more or less automatic because we know how the standard, we know these facts about the standard model of the standard model. And then we can also define lambda and application this way. Yeah, I guess I cannot go through all of this, but you can also define the universe. So this is just the universe. The computability predicate of the universe is just functions into the fibrant universe here. And then, well, I can flash a few other equations. So here I omitted the context here, sort of an element of a sigma type is computable if the first component is computable and the second component is computable. So this is kind of what you would expect. And the pass type, the computability predicate of the pass type is a pass type of the pre-sheaf topos of the underlying computability predicates. So this kind of works really nice. And you can also then define a filling operation, just using the filling operation of this A prime. So now this is where we need the fibrancy structure. And we can also define glue here, glue by sort of a similar thing. So there's one, one thing to note here, that the computability predicate for glue will also be a glue, and the equivalence you plug in here is somehow given from the equivalence here, but then you somehow have to come up with a proof that, well, this partial equivalence is actually an equivalence. So this partial function is actually an equivalence. And because we don't have any equation, I mean, it's not really, for this it's really important that we don't have any equations on how the filling computes, because I mean, I was trying to do this, some kind of parametricity interpretation of cubical type theory, where you also have to kind of provide, which is very similar to what I present right now. But there it's always important, because for the original cubical type theory, we have these equations on how composition / fill computes, and they have to be preserved. So they also have to be valid in the translated model or in the sconed model. But then it's really important what you put here, what kind of proof. And this was something which was, well, why I couldn't really directly prove some kind of parametricity result for cubical type theory. Anyway, now comes an important point, which is natural numbers. So, sorry, this is a typo here. So natural numbers are also interpreted as a pair. So this should be natural numbers of m. And then there's a computability predicate. And now this is interesting, because this n prime here is defined using an indexed inductive family over the closed terms of NUT. And the constructor of that is sort of means that it has, it's a family over bar n. So with the two constructors, so I have a proof that 0 is computable, and given that, sorry, this row should be not here. Given that n is computable, I have a witness that successor of n is computable. And now this guy has to be fibrant. And how can we justify that it's fibrant? So here is where we use identity types. So we can also define such a type n prime using parametrized inductive types. So you instead define a type n prime n, where you, for example, have a constructor which takes also an equality proof that sort of here all the occurrences of the targets of the constructors, they will all mention n prime n. So here not n prime 0 like here. So but it will take an additional argument, which is a witness that n is equal to 0 in this case. And we can construct these types, and for these types to be fibrant, it's crucial that we have the identity type around. And this is also gives also a nicer treatment in Mike Schulman's proof. So where he had to use to get the natural numbers working, he had to actually use to justify NAPTRAC. He was using a law of excluded middle order. Yeah. Right. But this works, and we can prove that this thing is again a cubical CWF, and I have 2 minutes left. Sorry, sort of projecting.
It's fine if you it's fine if you take 5 extra minutes, but generally we should be converging towards the end, not the beginning.
Yeah, I think I'm converging. Yeah.
Okay, cool.
Yeah. Right. So we have this gadget we just defined is again a cubical CWF, and we have a morphism of cubical CWFs, which is given by the first projection. And now we will apply this to get homotopy canonicity as follows. I mean, in the following form, sort of with the same assumption as before, as we had for the standard model. If we're given an element of NAT in the empty context, so context I'm referring to the model, the term model, we get a numeral k and the path that n is equal to this numeral. And how do we do this? So first, we'll apply this sconing construction to the term model. The term model is initial, so we get a map also from, so we get a section to the projection. And taking this n and we apply the section to this, we get something, I mean, the way how natural numbers in this T star were defined, they will give us a witness that n prime of n holds. And then you can prove by induction on this n prime n. So using the induction principle we get for these indexed inductive types, that we can actually get a numeral and a witness that n is equal to the numeral. And the way the identity types are defined, you could also get a path. And then we can just, this path also witness that n is equal to this numeral. So that's a quick sketch of how we use this then. Okay, so this argument can also be extended to identity types. So if we start with something like the notion of cubical CWFs, which has the structure of identity types, this works as well. Similar idea, again, somehow these indexed inductive types. And it also works for higher inductive types, or at least sort of those higher inductive types we considered in this recent paper here. Only given as CHM, this is our next paper. And we could also, instead of starting with cubical CWF, starting to require glue types, you could also require sort of that we have univalence is provable, or we have a term that the univalence axiom is inhabited for each universe level. So then this also works in this case. Right. Okay. So the stuff I mentioned before doesn't directly apply to simplicial sets. So if we start with C being the simplex category, I the interval, and F is, say, the sublattice of decidable C. So then these axioms are not satisfied. So this the interval is not tiny in this case. But sort of this is an argument, I think, by Christian, that if you assume the law of excluded middle, you can still get maps back and forth of this correspondence we had from before. And so you can actually do the same kind of construction as for the standard models before. So this also applies to simplicial sets. And well, here it's important that we work with that we assume classical logic. Right.
So before we go on, isn't delta 1 tiny because it's representable?
No, it's not, I think. Right, yeah. Because, I mean, in this case, I said before, you need that, you need something more. So you would need, for example, what happened in the CCHM cubic sets, you have the extra assumption that C is closed under products, which is not the case for the simplex category.
Okay.
Okay, so by an argument by Chris and Vladimir, we can see simplicial sets as a subtopos of cubical sets formulated with distributive lattices. And this correspondence gives also rise to a functor of these cubical CWFs. So you start with cubical CWFs over the simplicial sets, so where I, F, and C are like here. Then you can get a cubical CWF over, well, this cubical set structure, and hence this model from before induces a model in this, for this distributive lattice cubical type theory, where we don't have these computation rules for the filling, and which also is kind of an argument that if we have the corresponding cubical type theory, we cannot prove something, a wrong statement, because it will also hold in the simplicial set model. That's maybe something nice to know. Right. Let me now conclude. So we showed this homotopy canonicity for cubical type theory, where we took away the computation rules. So this was crucial for the argument also. Using the sconing construction. And one further crucial ingredient were the identity types, and this is wrong here. Right. And also assuming classical logic, we can do something similar to in a simplicial setting, but I think I stop now. Thank you.
All right, I'll now unmute everyone's microphone, and we're gonna thank Zeman for an excellent talk. So let's do that.
I don't think
And I'm gonna move on to muting everyone.
this part I was.
Okay, so everyone is muted, including Zeman, who I'm gonna unmute, and we're gonna take questions now. As in, he's gonna take questions, and I'm gonna just watch that happen. Okay, maybe I'll ask a question then. It's probably a very stupid question. So, is it the case? I'm kind of trying to come back to Ali's question. You have a hierarchy of a hierarchy of universes in type theory, and then on top of that you have types. So you have like U1, U2,
Yep.
up to, and then this is just cumulative, and there's no top level universe, but there's types. So all types live somewhere,
Exactly.
but not necessarily in a universe. And then on the level of models, that would correspond to a hierarchy of Grothendieck universes, and I'm assuming that there would be like a top level Grothendieck universe in that. So the hierarchy of Grothendieck universes then would be omega +1.
So, I mean, the U omega is really somehow to, well, let me go back to the definition of maybe, where was it? So for the definition of CWF, we basically start with n many, I mean, for omega many universes. So these are for each n. But we also kind of want something to talk about these gadgets here. So somehow we want to, for example, in the standard model, I somehow have to say, what are the types? So I have to write this down. And for this, I want to use U omega. I could also maybe define it externally, but this would be very cumbersome to write down. And it's also essential for the simplicial set model that you somehow let me go. Sorry.
Right, so in a simplicial model, you just have one more universe than you would have in type theory. So if you have a hierarchy, then you would, at least the way it's constructed in some paper, then
and that's the same here.
Okay, great. That was my question. So hopefully now someone else can.
So it's probably proof theoretically not optimal because we assume something extra. But
can you talk about? Sorry, go for your question first.
All right, I'm going to try to ask a dumber question. So you explained at the start that, of course, this homotopy canonicity and canonicity are different, and I think the obvious way is you've taken away the computation rules, right? So clearly it does. Now, however, in the model, right, you have these things that you say we're to think of as sort of proof-relevant witnesses to computability, right? In the tuples, that these things are carried with them. So isn't there a sense in which you could use those to then sort of extract a computation, or is that a purely formal intuition that I really shouldn't carry?
it's exactly what's happening here, right? So in the proof of this homotopy canonicity here, somehow this n prime here was a witness that n is computable, and this is where we extracted the numeral form. So this is where we got k from.
So then so in what sense can that not be used then to actually just give canonicity? Because there's a sense in which you have a computation and you extract a witness. So I'm obviously missing something conceptual.
Yeah, but I mean, canonicity would mean that there's a definitional equality between.
Oh, okay, so it's about the definitional equality with regards to the theory, whereas here we have the construction, but we can only observe it externally.
What we can do here is that we give a path, so it's not a strict equality. So this here we will have that n is equal to s of k, to the numeral k. But what canonicity gives you is that n is judgmentally equal to a numeral, which is strong.
Okay, I get it. Yeah, I see what's happening. Thank you.
So you're saying if you can have natural numbers that act like natural numbers, there's always a path between them.
Can you repeat?
There's a path to a correct term.
So if you have two kind of natural number looking types and they compute like natural numbers, then there is always a path between them. Or am I completely saying that wrong?
I'm not quite sure I understand what you mean.
Neither do I, to be honest. I had another question, actually. It's something you said about the simplicial set model near the end. Could you repeat that?
Sort of the gist of it is that there's also some kind of standard model of this simplicial set situation, or so we can do this, what I sketched in the standard model section, also for simplicial sets, if you assume classical logic. And there's a connection between simplicial sets. I mean, on top of that, there's a connection between simplicial sets and certain cubical sets. And now if I look into this particular cubical set, so these are cubical sets based on distributive lattices, and I can look at the underlying type theory. So I also have type theory T in this case, and I know that this has a model which comes from the simplicial set model. So if I look into this, what I can derive, I cannot derive something which is not homotopically different than what happens in the standard model. So somehow it says that I cannot derive something wrong about, or wrong in the sense of the standard model or simplicial set model in this particular cubical type theory.
Was that the last thing that you said in the talk? Like, was that the second to last slide? So yeah, that one, yeah.
What about it? Or?
So if you have something in cubical sets, as long as you have the standard model and simplicial sets, it will. Oh, maybe. Wait, don't worry.
So I mean, let's make an example. So for example, I could prove that a certain homotopy group of some spheres is Z modulo 3 or something. And now I know that, I mean, this is now the proof in syntax, right? But this also has to be true in the simplicial set model, because I have from the term model, I have an interpretation function into this model induced by simplicial sets. So it cannot have a different homotopy group here. I mean, if it's...
Because that's the thing that was kind of surprising for me. So if you have something in the cubical set model, let's say if you prove something in cubical type theory, it works in the simplicial set model. Is that what you're saying?
So if you prove something in a certain cubical type theory where you don't have the computation rules for the filling operations, which is not the cubical type theory which is implemented, for example, but I mean, it's a variation thereof. Yeah. Then this also has a meaning in the simplicial set model. And also, what I forgot to mention, I think Anders also experimented with this. I mean, he took away the computation rules in cubical TT for took away the computation rule for composition, and then actually quite a lot, most of the files still type checked, which is surprising that somehow these definitional equalities are actually not that important. What is a bit cumbersome is to prove univalence still. That's something which is somehow a bit difficult if you don't have these computation rules, but it's still possible.
If you take the computational part of cubical type theory out, what do you get left anyway? I mean, there's not much difference between that and the simplicial set model in my head. I don't know.
I don't understand you. Sorry. What do you mean?
Maybe I'm misunderstanding something.
All right, we'll wait for a few more questions. So a couple of minutes. So I don't know. All right. Well, final call for questions because we need some questions. So you should ask questions. I think that may be a sign that there are no more questions.
I mean, I might have one more little question.
Okay.
Sure.
But one of the things I kind of felt uncomfortable about when learning about cubical type theory is that if I do something in cubical type theory, like calculate a homotopy group, how do I know how valid that is in, like, you know, book hop?
That's an open problem.
So that's why I was a bit confused when you said that at the end, because I thought you were.
Yeah. So I mean, what is what I said here in the end? If you implement something in cubical type theory, which doesn't refer to the computation rules of the composition, then you can at least not give the wrong homotopy group. You cannot calculate the wrong outcome. Does that clarify the situation?
I guess it kind of clarifies it, but when you don't use the computational stuff in cubical type theory, you know, is that even that different from book hop at that point?
Well, you still have, it's still quite nice to be able to argue with the past types. I think that's kind of, if you argue about, I don't know, it's easier to use these kind of, or I don't know, I mean, this is kind of not very substantial, what I'm saying now, because maybe we have to experiment more with formalization there, but I think kind of in general, I would say that having access to these path types and being able to define a path just by basically lambda abstraction really gives you a nice way to talk about the higher dimensional objects. And then, I guess sort of coupled with the, for example, the path types or even these extension types like they have them in RedTT, I think that really simplifies things quite a lot to formalize.
All right. Thank you very much. There's a question in chat, by the way.
Does this give us any insight into solving original Vladimir's conjecture? Vladimir's original conjecture. Not directly. It's probably you can prove the Vladimir's conjecture once you can define this global section functor valued into simplicial sets. And then you can apply probably some very similar technique, or what basically use Mike's argument then. But how to do that is not quite clear to me.
Maybe, sorry, I'll make a comment about the earlier question, because so it's unclear to me what it means to remove the computational stuff. And I mean, there's more into cubical sets than whatever the computational stuff would be. So
yeah,
the cube category is a Lavier theory, whereas the simplex category isn't. So there's a big difference there in terms of like how easy it would be to even write syntactic expressions. I think.
Right.
All right, so there were questions. So I know, okay, final call for questions from those who want to ask questions. And maybe I won't be wasting too much of your time then by repeating calls for questions. So this is the final call for question. And if there are no questions, I'll unmute everyone's microphone again, and we're going to thank Zeman again. All right, and off we go. And I'll mute everyone again. Yes, okay, perfecto. So we're going to meet in 2 weeks for another hot test. Thank you all for joining.